Next BMS NEMO, and all of them dedicated to propelling the advancements in the next generation battery management system technologies. The Alliance aims to develop the new next generation battery management systems, leading to enhanced performance, lifetime reliability, safety, and overall optimization utilization of the battery systems. Today, you will hear 4 presentations showing data access and data harmonization from the 4 research projects of the Alliance. We will have 2 Q&A sessions, one after the first 2 presentations, and the other one after the second batch of the presentations. For the Q&A sessions, I would like to ask you to type your questions into the chat. You can type it even during the presentations, and we will take them all together during the Q&A session. And when you type your question, please indicate to which speaker, to which project your question is addressed to. Before we start, I would just quickly draw your attention to this symposium on emerging battery technologies that will be held in June in Oslo. And in conjunction with this symposium, there will be a one-day BATMO workshop on the 13th of June, where participants will get hands-on introduction to the software and learn how it can be used for battery simulation and optimization. So if you're interested, you can find more information on the link. And now I stop sharing, and I would like to ask the first presenter, Stefan Walter from Fraunhofer Institute, representing the BATMAX project, to start the presentation. So Stefan, the floor is yours.
So, hi everyone, I hope you can see the slides. Just a short checkup?
Yes, yes.
Okay, perfect. So, my name is Stefan Walter, and I welcome you to my presentation with the lengthy title, Unleashing the Potential of Battery Data, Transforming Measurement Data into Strategic Insights for Battery and Battery System Optimization, as part of the BMS Alliance webinar. I'm a senior engineer at the Battery Systems Group of the Fraunhofer IISB. And let's have a short look what the Fraunhofer IISB is. The Fraunhofer Society is one of Europe's largest applied research organizations with around 32,000 employees. That includes scientific, technical, and administrative staff. The Battery Systems Group, where I'm working in, is part of the Fraunhofer IISB in Erlangen in Bavaria. That's the Institute for Integrated Systems and Device Technology, in short, IISB. The Fraunhofer IISB has 2 large research fields. One is semiconductor technologies, and the other one is power electronics, where the Intelligent Energy Systems department is located in, and the Battery Systems Group is also a part of that department. So, what are we doing in the Battery Systems Group, and how does this doing reflect our sight on battery data? We are developing battery systems as a whole, so our chain of economic value added starts from the manufactured cell, and then we integrate these cells into battery systems where we do all the layout and design and assembly. So in detail, that means we assemble cells to modules, to packs, and to entire systems. We develop the battery management system electronics and the accompanying software to measure all the battery data and battery system data, and use that to control the entire battery system in combination with the higher level control unit, for example, the VCU. So that includes controlling the flow of power through the battery junction box, the thermal management of the system, charging through modeling and simulation algorithms, and all that we are doing in our team. So basically, we start from the cell, and in the end, we have a battery system and we gather lots of data from the system during the engineering phase, and when it's then actually running in the field, in the application it was designed for. So what does battery data then mean? There is lots of different battery data. Battery data is collected under very different conditions, aspects, and it's also collected for different purposes. And this leads to a great different set of data and great difference in quality of the data. On the one hand, you have laboratory measurements that are needed for detailed characterization of the cell, modeling of the cell during the design phase of the system, or for safety evaluation purposes. During these tests in the laboratory, the quality of the measurement data is typically very high, as you have sophisticated and well-calibrated devices. The conditions where the measurement data is acquired is well known. So that's one part. And on the other hand, when the battery system is in the field, there are typically way less sensors and way less data for the specific data points. Nevertheless, this data still needs to be acquired for operational purposes and then stored and evaluated to, for example, evaluate whether your system behaves in the actual environment like it was designed to, and you have the ability to improve things in your next design. So now let's have a look at what this battery data can, for example, be. In any case, battery data basically always is time series, and you have at least current, voltage, and temperatures acquired. But there can be, of course, lots of more different data. For example, you can have electrochemical impedance spectroscopy, you can have deformation information or pressure information. So we cannot be sure that all this data is always the same. When we have a look at the laboratory measurements, the measurement data is typically regular time series in a well-structured format, whereas in an application, the data can often be irregular time series, and the format is not always structured, but typically semi-structured data. I said you have typically less information in the field compared to the laboratory, but that's just for specific measurement points. In the end, due to the number of systems in the field, the amount of data measured by a BMS in the application will then typically be far bigger than the laboratory measurement data. So you have quite different data, but you have lots of it. And this, among other things, makes storing and analyzing the battery data challenging. So what is the objective we derive from that? We need to provide a toolbox to transform different battery data into a format that enables the analysis of the data. Let's have a look at one example for battery data from the field. So we have a classic BMS output in form of a CAN log. That's an example from our open source BMS solution, Fox BMS. The BMS communicates with the higher level control unit, let it be the VCU, for example, via CAN, and transmits all its battery measurement data with a data rate something between 20 and 50 Hertz for cell voltages, temperatures, and battery current on the CAN bus. Then, for example, you have typically a battery voltage measurement that has accuracy better than 1 millivolt. All these messages are time-stamped, and you have a semi-structured format in your CAN log. The time interval between the individual CAN messages varies by a few microseconds. So it's not strictly regular, well-formatted data. So what's the first goal? We need to transform this kind of data into a structured format that is machine-friendly to work with when we want to analyze it. This is an example for, again, Fox BMS log, but you have to do some of the same steps. For example, if you have a log or a CSV file from a measurement device. So what do we do with this Fox BMS data then, or the CAN log data with our Fox BMS attached? We need to filter all the irrelevant CAN messages on the CAN log, for example, other measurement devices on the CAN bus, control commands for valves or something like that. We need to filter all that out. We need to decode the logged CAN messages into a machine and human readable format. For that, we choose JSON as an intermediate format. Then we can group the decoded CAN messages together with respect to their CAN identifier, so the specific information it stores, which then leads us to a state where we have multiple regular time series. Then for the analysis of the data, it is of course favorable to combine all these different time series from their specific CAN identifier to one large time series by synchronization to include all the relevant information at a specific timestamp. For battery systems or battery applications, synchronization with respect to the current is a reasonable choice typically. And that's what we use in most of our use cases, but this can, of course, vary dependent on your specific use case. So where to go from here when we have now a well-structured and well-understood data? We use a concept called ETL, extract, transform, load. ETL is a data engineering concept to automatically pre-process data from various sources and upload this data to a central data storage. This data storage can be a database, a data lake, or a big data framework that allows you to analyze this data. At Fraunhofer IISB, we have developed an ETL engine for battery data that is configurable for different data types. And this framework will be part of Fox BMS 2. For example, we are going to support data sources like CAN logs and data from MQTT or structured file formats like CSV or Parquet files. And additionally, a mechanism to upload this data into various databases and export the data to different file formats and frameworks. Again, this framework and its documentation will be open source available as part of our BMS solution, Fox BMS. Now, let's then dive into the detail how this is implemented from at first at a high-level perspective. We have our decoded battery data from different sources, but in a well-structured way. Then we need to serialize the data that allows us to handle the data in memory for a fast and efficient access. And then we need to somehow clever distribute the data and the analysis tasks we want to run on several workers to have an efficient analysis of our potential very large data set. So what are the solutions here? We first need to understand that battery data analysis basically always requires data queries that affect many values, but only from a few columns. This makes using a column-oriented data structure reasonable to achieve high performance when handling large data sets of that type. Our goal was then here to implement a solution that is based on open source tools that supports different programming languages, as the pre-processing tool should offer a comprehensive support for different programming languages due to the heterogeneity of tools, applications, and the data. And again, we need a tool that can handle large data sets well in a performant way. So let's have a look at the first part, storing the battery data on a file system. We choose for that task Apache Hadoop. That's an open source framework providing a cluster-based file system called HDFS and a cluster-based batch processing engine MapReduce to process data with tera or even petabytes. So we have the first part of the solution. Now we have to handle a large amount of data in memory, and for that task we choose Apache Arrow. Apache Arrow is again an open source, language agnostic software framework for developing data analysis applications that process columnar data, what we have, and we can use our battery measurement data on that. We have interfaces to C, C++, and popular languages like Python or MATLAB, so it makes it well suited for our process. Next, we need a tool that lets us analyze the battery data efficiently. For this task, we choose the open source software Apache Spark, which enables us to do the following. Divide tasks like analyzing application data, training or running models into different subtasks and distribute this work between multiple processing nodes. Again, we need to do that because we have lots of data. Further, this approach lets us execute those tasks even on single node machines, but also on clusters. So it's friendly for development workflow. You can use it locally and then put all that work on a large cluster. So what do we have in the end from all that data storing, analyzing, etc.? We are generating lots of measurement data. We can process and store this information with our framework. We've implemented a tool to visualize that data generically. As when you see typically things, you get a good idea what the data wants to tell you. We can transform that data from our learnings to a knowledge database. We can put the data in a structured way in this knowledge database. We can feed the data from the knowledge database, from our logs into battery and battery system models. And the combination of battery system models, the output of it, and the knowledge database can be automatically used for battery system design, which then results in an application. And from that application, you again get back relevant information on the battery system behavior. So you have the feedback loop closed from collecting battery data to making battery systems, and by the feedback loop making battery systems better. Then I would like to thank you for your attention and happy to answer your questions later.
Thank you very much, Stefan, for this interesting presentation. Yes, we will take the questions after the following presentation. Again, just to remind you, you can type your questions into the chat, indicating the speaker from which you would like to ask the question. And then we will take it for the two projects in the Q&A session after the next presentation. So with this, I would like to give the floor to Aurelian Hascott from EDF, representing the Energetic Project. Aurelian, the floor is yours. Aurelian, we cannot hear you. You're muted.
Is it okay?
Yes, now okay, thank you.
Right. Right. I just said I want to thank you for inviting me for participation to this webinar, and I would want today to introduce you the view of EDF on the data access harmonization, and of course also the different works which are performed in energetic project. So just for entrance, I would want to show you the global footprint of EDF Group in the energy storage in the world. So we have a huge quantity of projects and also a huge quantity of storage. And I want to show you an example of a storage actually. So more than 3,000 megawatt hour of storage. 12,000 racks, 700 containers of batteries, and about 13 millions of cells. And we have to manage, just in this example, we have to manage all the cells, the modules, the racks, and the system. About EDF, I work in the R&D department of EDF. EDF means Electricity of France, and we are the main company of electricity in France, of course. And this enterprise have his own R&D, and for that reason, we can make prospective test modeling and also project support. So we test the different cells or modules in terms of performance, security, etc. We also have a view on the coming technologies on the market in a few years, and we also can test performance and modeling, security modeling, aging, and we can build different kinds of models in order to secure the different investments, which are very important for that kind of subject. But we also work on the mobility because of the huge experience we gain in the field of the stationary storage. And to say you, we know that if you take one cell, three cells, but with the same characteristics, and you apply three different solicitations, you will have three different behavior in terms of aging. And it's known today that the electric vehicle manufacturers propose a warranty on their batteries, and this warranty is mainly, so it's written in French, but it's also clear. This warranty is a 8 years warranty or 160,000 kilometers. And so it can make a problem in trust for the people who are supposed to buy and use the electric vehicle, particularly in the field of the European Union and the introduction of the selling electric vehicle after 2035. But today, I have to say that there is not standardization or regulation in the SOH. SOH means state of health. So this is the measurement of the remaining capacity or the remaining energy, or perhaps the remaining lifespan in your batteries today there is not standardization or regulation. If we have a look on the UN Global Technical Regulation, it's said that you can do what you want. There is not one way to test, and all the ways are allowed. If I think previously about the warranty of the car manufacturers, it means that a car manufacturer can choose the way for him to define the SOH and so to define the way to say that you are at 70% of SOH or below or beyond. And about the European regulation, the regulation is actually in progress, of course. And the battery passport will impose to give an information name SOX, so it's linked with SOC, the state of charge, and SOH, the state of health. But there is not a regulation to express it in ampere hour, kilowatt hour, or perhaps time. And it's not imposed also to give some time series linked with time of course, temperature, voltage, current, etc. So it's not an obligation, and it will be not an obligation for the manufacturers to give an access to the data, to the raw data. But it would be very important to be able to have a precise and an accuracy view on the state of health, because the battery represent at least 40% of the value of electric vehicle. So this is actually the most important in uncertainty in the value of the electric vehicle market on the second hand. And EDF R&D is involved, of course, in different European projects, BATMAX, BITLIP, Next BMS, and Energetic. Energetic is the project in which I'm personally involved. And so in this project, our aim is to test, develop and test the new sensors, and use these new sensors, and also, of course, the typical sensors we can find in the market, in order to train artificial intelligence, and then use the artificial intelligence to put more intelligence in the BMS, in order to allow a better monitoring in kind of lifespan, of course, but also safety and optimizing aging and the different ways to monitor and to monitor the batteries. So I won't say what data access can allow for stationary and mobility applications. In kind of monitoring, the system needs to be monitored to ensure the service. For example, I show you the huge PV storage previously, and we are engaged in order to give a service in kind of time, in kind of energy, in kind of availability of energy. And so it's essential to have the good monitoring. and of course to secure the battery in kind of lifespan, because the investment are also huge, and it's important for us to have a good lifespan more than 10 years in that kind of project, perhaps 20 years, for example. It's depending, of course, on the different projects and the sizing. We want to allow artificial intelligence optimization in order to optimize the monitoring, also the safety. It's very important today because many examples of a fire are existing today in some in Europe, also in Australia, and in United States, of course. And we have to have different kinds of strategy in order to avoid as more as possible the safety problems, and also to allow the BMS to become updatable with it would be it would be perfect if we could do it in a real time and with a custom battery steering. And that kind of thing are made possible by introducing IA in the BMS, because the BMS will be able to learn during the exploitation time of the battery, and so he can himself update this the optimization of the service, of the safety. That would be really important, and it's not done today. The value estimation, of course, is, for example, if I don't only speak about the stationary storage, is for leased vehicle or for the second life applications, of course, because today it's very complicated to have an accuracy view on the state of the battery from the first life. And so it's perhaps a more dangerously in terms of economic view, but also in terms of safety view. That is an explication today about the poor number of second life applications in Europe, and which has the energetic contribution in that access. So we are developing, I said, new sensors, also performing aging tests at EDF R&D for in order to train artificial intelligence, and we do it with a profiles, typical laboratory profiles, of course, but I will show an example realistic also. And we are going to produce a proof of concept composed with a BMS with IA and a real battery with 12 batteries. So and why the harmonization is a key point. So about the data volumetry, this is a very huge volumetry. I let you imagine the volumetry of data with more than 12 or 13 millions of cells, with the modules also, and the racks, and the containers, and the cooling systems, etc., etc. It's very, very important, and the data must be compressed, stocked, and stored by the system locally or online. And different ways to do that is using turning tests. And also I can talk about the CCI 61 850. and in order to allow also a best analysis, because it would allow us to anticipate the maintenance operations when we have to change one module, for example, or when a part of the cooling system have to be changed, for example. And also it will allow to optimize the availability and the safety. And it could have an impact on the sizing of the system, for example, if we need to make a less upsizing of the system. And it will allow also to introduce new test methods that we currently use in the laboratory. ICA, I think about ICA, for example, and they could be used and by the IA in the BMS if it's possible in of course in term of the quality of the different measurements. And just to show you, this is an example of the right of typical pattern of a Londonian electric bus doing 1 day of exploitation.
Aurélien, I just want to let you know you have 1 more minute if you can conclude.
Okay.
Thank you.
This is the last. So what is the situation today? So actually, we are operating a stationary application, and it's easy to access and to access and to make the harmonization of the data, because it's our own data. But it's not so easy in the mobility field, because data producer and car manufacturer is mostly different than the owner. And we don't have an accurate estimation of the SOH. Just to give you an example on the right, we measured the capacity of different cars. So by charging them from 0 to 100%, and we did it at different temperatures in order to reduce the uncertainty. And we took from the BMS the information of the remaining capacity, the SOH, and we saw a significant difference between the BMS information and the measurements. And so what have to be done? European battery passport will communicate only on the SOH and SOC. It's not enough to have an accurate and give trust to the users. Also, raw data as time, current, voltage must be available in order to make that kind of measurement, and also to train an IA. It will be important in the very soon to define the one way to measure the SOH, and in order to improve the trusting of people. And in energetic, we work in synergy with researchers, startups, and the industry that I represent currently, to develop and integrate the IA in the BMS. Thank you.
Thank you very much, Aurélien, for this presentation. I cannot see any question in the chat, and because we are a little bit above the time, I would suggest to proceed with the next 2 presentations, and then we will keep the questions for the end. So with this, then I would like to give the floor to Bernhard Lutzer from TT Tech, representing NEMO project. Bernhard,
yes,
the floor is yours.
Share the presentation.
Yes.
Do you see my presentation now?
Yes, thank you. Yes.
Great. So thanks for the warm welcome, Melinda. So my name is Bernhard Lutzer. I'm representing the company TT Tech in Vienna, in Austria. and I will present today our findings from our project NEMO. So NEMO is a new project like the others, and our aim is to advance the modeling we mentioned today. It's led by the Free University of Brussels and has partners like us in the field of software, partners in the field of batteries, BMS systems, and hardware. As for the other projects, data plays a very central role for us. Therefore, harmonization of data is a big topic for us, as many partners in our project provide data, and we need to somehow unify them. I will show you some examples of the issues and best practices we had, which I think are quite useful for batteries. All of that are based on electrical impedance spectroscopy. I wasn't exactly sure about the audience, if everybody knows that. I just have one slide that it's an important technique to measure the electrical response for batteries across different frequencies. And this can help you to have a better understanding of the situation of the battery. So it has been talked before on the other presentations, so I think we can go over this slide. In our project, and I think in many others, several partners gather data. And in this case, I'm only talking about electrochemical impedance spectroscopy data. There's other data in our project which is also gathered, but I don't talk about this today, but the challenges are very similar. We have TU Graz, we have the University of Brussels, and we have CSEM in Switzerland. So each of these partners makes principally the same measurement, but they have different measurement instruments, manufacturers, types, ages. Anybody who knows electrochemical impedance spectroscopy knows there are Zana and Biologic and whatever, many different manufacturers who should in principle all do the same, but in reality are different. There are different operators. So is in research projects, there are often students involved. Students stay for half a year, then change, or people leave, can happen in companies as well. This also means maybe data is stored differently because it's somehow also a personal flavor, if you don't define it. There are different types of measurements with different goals. So even though it's the same measurement type in spectroscopy, you can have older cells, you can have it in a thermal chamber, you can have it under mechanical stress. And typically all this data is stored in a different format. I mean, it's stored mostly in files, in CSV files, as mentioned before, but there can be different columns, different rows, different data types. But in our project and the other projects, they need all this data to develop better battery models. So the question is how we can achieve that, how we can help the people who are modeling data to have a better overview of the data. Here I have a more clear overview of the more detailed overview of the issues we really encountered. So this is really stuff we had in the project duration for now. As I said, different ES companies, different data formats, different metadata, data processing inconsistencies. So there's even during the measurement campaign, sometimes data formats change. We have missing values. We have different frequency and time resolutions. This is also a big topic. We have different output structures, and it's sometimes quite difficult to compare across measurements. Even though they have the same instrument in different locations, we still see difference in the data. Also something which is for me was unexpected, but now I am in the project, I learn more about this. They're not only technical challenges, but also, I call it unexpected and non-technical. There's a difference between how chemists, mostly chemists, are doing these EIS measurements and IT specialists. This is really, because chemists, I don't want to insult any chemists, but typically they're not experts in IT systems. So they just store the data on the computer, they have it in a folder, somehow structured, and then they send it to me. And in many cases, they don't care about data integrity, about backups, metadata sometimes. So IT specialists who take care about storing the data numbers, they need a clear structure. They don't like changes in data format, which a person who just deals it personally knows, I changed the data format. They know it in the heart. and they're quite concerned about how the data is kept in a good order and not lost. So something we learned is that clear communication is key. Best is to have somebody who understands somehow both worlds. Maybe I'm a bit lucky because I'm a physicist by education who did ES measurements many years before and now working in IT. Best would be that somebody who understands somehow both worlds, but I know this is not always possible. Just show you an example of data representation issues. Anybody who knows complex numbers, so impedance spectroscopy, for them it's just something already known. You can have the impedance value represented in two ways. You can have it as an imaginary and a real value. You can have it as the absolute value and the phase angle, which physically is exactly the same, but one instrument stores it in format A, one format stores it in format B. If you give it to somebody who has no idea about ES, just sees, these are different columns and they have nothing to do, so I store different columns, which makes it difficult for the people in the end who are doing modeling, because I mean, in many cases they know, but then they have to do the data transformation on their own. So something how to do the data conversation and knowing what can be converted to which, because most of the stuff we are measuring are some physical measurement values. This is a big challenge in data harmonization, especially in our case. So what do? We have defined a unified database scheme where we are separating metadata from the measurements. I think this is good practice. This is nothing which we invented. So we can ensure the relational integrity for the comparison. We have for each of the data providers, didn't work out to force the people, not force to try to people to give you the same data. This doesn't work for many reasons. So we accepted the data conversation, the parsing has to be done by the ones who are storing the data, which are us. So we developed parsing scripts which read and standardize the CSVs and handling all the missing metadata and whatever problems we had. And we have an automated process in place, or we're still working also on it because the project is still ongoing, and trying to improve it, to have a pipeline which is based on Python to handle the data, in the end stored in a SQL database. So the data structure is just an example of how we store the data. We have it in a centralized database. It's principally so we store it in a so-called timescale DB, which is PostgreSQL with a plugin who helps us to better perform time series measurements. I think it would in principle also work with a normal SQL database. It just makes our life a little bit easier. Storing in a centralized database helps us to have a structured and scalable data management, and we can query across multiple experiments. We're just storing this in one database because from what I learned within the project, what the others provide, we are not in the field. So we don't need any distributed architectures. So if we would have needed that, we would have changed to that, but this is not needed for now. So this is just an example. Anybody who has seen databases know you have separate tables for metadata measurements, and you're linking this with a key so you can extract the data. So here's also the workflow, again in a little bit other structure. So extract the metadata from the different file formats. We convert. The conversion mostly happens on the impedance data. So temperature and all that stuff doesn't need to be converted because we get it in the same form. Then we store it in this database, and in the end, people can query it and can make their own visualizations and use it for the modeling. As I said, we have the database where we store it. We have a so-called Nemo Cloud, as we call it. This is based on Microsoft Azure, which is quite well known. It's the cloud service from Microsoft. We are maintaining a cloud instance for Nemo based on that. The reason why we are doing this in the cloud, it's quite easy to set up a database in the cloud with very little effort. You don't have to take care about many of the security issues when you have your own server. anybody can access it. So we have different partners in different countries, so people can just access the server and push data to the server. So this cloud-based approach helps quite a lot, and it's not too expensive compared to the amount of work you don't have to do. So this contains about the central database. Then we have cloud file storage. So people don't push the data directly into the database. We tried this, but this also didn't work because I had to explain too many things. So in the end, we agreed that people push data to file storage. Some of the people push it just manually when they made a couple of measurements. Others already implemented some automated pushing pipeline. I don't care, it's their work. I would automate all of them, but always you have different partners, different levels of IT knowledge, so whatever they want to do is what they do. Then we have some data ingestion procedures which are serverless. Serverless is just a quite modern concept where you don't, for scripts and for stuff you regularly do, you don't set up a VM instance for that, but you rather push the code to this Azure. And also, which is part of the project, but I don't talk so much about now, is that we also want to push models, so battery models, into the cloud to execute them there. But this is something we are doing in the last part of the project. So here you can see just this data ingestion pipeline again. So the BMS produces the data, it's stored locally, then it's pushed to us here in this cloud storage where files are stored, and regularly with cron jobs, so with just a function who helps to execute things in a timely manner every day, every hour, something like that. It's pushed in. From data harmonization, quite common issues we face is this inconsistent metadata storage. So people store the metadata inside the CSV. Some store some metadata in the file name of the CSV. Some store it in some text files. I've seen everything basically. Yeah, we had some missing values requiring interpolation estimation. It's mostly when sometimes it happens that there's not a value in the CSVs because for whatever reasons the measurement instrument doesn't produce anything. We have these issues with different infrequency points across data sets. So they have different steps in which frequencies they do the impedance measurements. So as I said, best practices. I try to push to the people to use a common naming convention, which helps them when you have also defined the metadata in a certain format to have an automated metadata extraction. And as I said, we define the unified impedance representation. There's also the question how to make the data accessible. I mean, inside the project, it's quite easy to be accessible. People get the possibility to query the database with SQL. SQL is quite easy to learn, and even if you don't know it, there's the help of LLMs. So even if you never programmed, it's quite easy to write SQL statements with the help of ChatGPT. But there's no help for people outside of our project because I cannot give the whole world access to our SQL database. So what we want to do is to store the data in the end on Zenodo. But there is one issue. At least to my knowledge, there's no standardized EIS data ontology. If you have some, please tell me afterwards in the comments. So in the end, what we do, we will publish the results at the end of the project in our own ontology, which we defined in the project. So just some key takeaways before I end the presentation. So data harmonization is very essential to have a meaningful battery model. Because you need the full picture of what is happening within the projects to have enough data to make a good model of the battery. I mean, you need early standardization efforts to reduce the manual analysis time and improve the component. The ones who are creating the data and the ones who are transforming and using the data. And in the end, I mean, this is nothing new, but this is true as well. Automation helps a lot in scaling the data handling that you don't have to do a lot of manual works. This was my presentation. Are there any questions left? Right on time, 15 minutes and 18 seconds.
Thank you very much, Bernhard, for this interesting and really very practical presentation. And then I will give the floor now to Viral Vadavia from ABL, representing Next BMS. And afterwards, we will take the questions. In the meantime, if you have any questions, you can start typing already into the chat. Vera, we cannot hear you. You're muted.
Not unmute myself.
Yes, now we can hear you. Thank you.
Okay, yeah, that's great. So hello everyone, my name is Biral Badavia. I work at AVL Software and Functions GmbH. AVL Software and Functions is based in Regensburg, Bavaria, in Germany, and it has the focus on technologically leading software and system solutions for intelligent and ecologically compatible mobility, as well as the system integration and electronics development. AVL has been designing and improving all types of price systems for years and is realizing the new visions for the future. I will give you a presentation on BMS and the cloud for next BMS project. We aim to unlock the intelligent, decentralized, and adaptive battery management system with next BMS. So what are the ambitions of next BMS? We aim the global shift towards battery electric energy storage spans not only the consumer products, but electrical mobility and stationary storage energy storages. This transition demands advanced battery management solutions for efficiency, longevity, and performance. The project objectives of Next BMS is to develop innovative battery solutions to support widespread adoption, enhancing efficiency, durability, and sustainability of battery technology. And we focus on mobile applications like long-range electric vehicles and stationary applications, enabling grid balancing and energy storage from variable renewable resources. The key focus areas are to improve battery lifetime by enhancing battery longevity, by optimizing both cyclic and calendar life, to innovate battery chemistry, improving material composition to boost performance and durability, to cater challenging use cases by developing solutions to manage high stress electrical load conditions and bring hardware improvements, advancing sensor technology for more accurate battery monitoring. Also do the software innovations to refine battery models to improve state estimation and control algorithms in BMS. By addressing these focus areas, Next BMS optimizes battery performance, extends lifespan, and supports a cleaner energy future. What are the technical ambitions of Next BMS? Since the dawn of technology, efficiency has been the driving force of progress. Next BMS carries this principle forward by enhancing electrical efficiency and battery longevity for both current and future systems. Our approach combines physics-based modeling with data-driven intelligence, refine battery behavior, improve state estimation, and ultimately maximize performance. Beyond just the technical advancement, Next BMS supports a more sustainable energy ecosystem, minimizing environmental impact while ensuring optimal efficiency for mobile and stationary applications. This enables the following key benefits. It helps in extended battery utilization and lifetime, expanding the usable SOC window, increasing full equivalent cycles, and enabling faster charging to enhance real-world usability. This means not just longer battery life, but smarter energy utilization, extracting the most from each charge cycle. Accelerated innovation and time to market. Next BMS facilitates the rapid development of new battery packs and ensures seamless integration of an emerging battery chemistries. Enhance safety and reliability. Batteries must operate reliably under demanding real-world conditions. Next BMS ensures robust performance while improving end-of-life management, enabling safe and second life applications to extended sustainability. and also optimized BMS performance. We are demonstrating a fully functional battery module with advanced state estimation, intelligent control algorithms, and cloud-based enhancements. Optimized BMS performance means not just longevity, but also adaptability, smarter, safer, and more efficient operation. With Next BMS, we are not just improving batteries, we are redefining their role in sustainable energy future. By combining physics-driven insights with machine learning capabilities, we push the limits of what's possible in battery management, delivering efficiency, reliability, and sustainability at energy every level. What we are doing in Next BMS is we are decentralizing the BMS. So traditional BMS architecture are centralized, which limits scalability, adaptability, and advanced analytics. In Next BMS, we introduce a hybrid architecture, distributing intelligence across multiple layers for better performance. So the key components of hybrid BMS is local BMS, which handles real-time data acquisition, safety, and control at the battery level, and the cloud BMS, which leverages advanced analytics, machine learning, and fleet-wide optimizations to enhance battery performance and lifespan. There is an IoT gateway in between, which bridges local and cloud BMS, which enables bi-directional communication for real-time insights and adaptive control. The benefits of decentralized BMS is seamless collaboration, scalable, scalable physics-based models, which improves SOX estimation accuracy across different battery types, predictive maintenance and safety, which detects thermal runaway risk and estimates remaining useful life. Life cycle-based BMS calibration, which is optimized battery management at beginning of life, mid of life, and end of life stages, and data-driven optimization. By decentralizing BMS, Next BMS unlocks the next generation battery intelligence, ensuring longer life, battery safety, and improved efficiency for both mobile and stationary applications. How we approach this? So we define the cloud-based BMS interface to enable the seamless data exchange. So a successful BMS requires a strong cooperation between hardware, software, and the cloud integration to enhance efficiency, scalability, and adaptability. Next BMS follows a hybrid architecture, combining onboard intelligence with cloud-driven optimizations for real-time battery management and long-term performance improvements. Cloud intelligence, which enhances the BMS intelligence. So traditional sensors such as voltage, current, temperature, and some additional sensors, strain and CMB, feed real-time data to the BMS. A dedicated edge device connects the BMS via CAN and enables data transfer to the cloud. Once data reaches to the cloud then can further process the data. On the BMS or embedded side, there are some models which are running. So Next BMS run adaptive models on both the levels. So onboard BMS, so it executes lean AI models, state estimators, and adaptable physics-based models for real-time control. And the cloud counterpart of it processes high-resolution data and refined state estimators, adaptable physical model and degradation model, RUL model, and aging predictions. The bidirectional learning refines the parameter and transfers them back to the BMS via the IoT gateway. By combining modular hardware, scalable software, and cloud-driven intelligence, Next BMS enables real-time battery control with advanced onboard algorithms and predictive maintenance and safety through cloud analytics. Now let's talk about the Next BMS project, which enables seamless collaboration. First of all, the next BMS collaborative cloud infrastructure is designed to streamline data sharing, model development, and real-time collaboration across multiple partners in the consortium. However, something that is often overlooked in this project is like how difficult and important it is to harmonize data across different teams and systems. There is a significant challenge in ensuring the data from various sources is consistent and usable by all partners, which is critical for smooth collaboration. We also heard from NEMO project that how important it is. In this project, we use the IoT gateway to capture the high-resolution BMS data in real time. I have this device with me here. Once the device captures the data, it pushes the data to the cloud in real time. It's available instantly for testing and adaptive tuning across different locations for partners. But as you can imagine, the real-time data sharing requires careful attention to make sure everyone is speaking the same data language. When you have partners in different locations using different systems and equipment, harmonizing data becomes a challenge. This is where this platform comes into play. It helps streamline validation process and accelerates the innovation cycle because everyone has access to the same consistent data. A lot of other partners perform different tests, and then they can upload their test results alongside the BMS data, and the other partners can access it. One salient feature of this architecture is also the giving updates back to the BMS. So all the different partners can develop their model, they can improve on their model, and then they can also write back the parameters, which goes through the cloud pipeline and then writes back to the BMS to update the onboard machine learning models. In conclusion, while the cloud collaboration framework certainly accelerates the development and testing, it is the harmonization of data that's truly the backbone of this project. I'll give you an example as well. Traditionally, the systems use techniques like Coulomb counting, lookup tables, and equivalent circuit models to estimate SOC. So these methods are limited by prior knowledge, leading to longer safety buffers, reduced performance, and higher cost. Next, BMS takes a different approach by using physics-based models. These models factor in ionic concentration, diffusion coefficients, and reaction kinetics, allowing more precise control and better performance. This improves accuracy, reduces the need of extensive testing, and enhances battery lifespan. For example, anode potential modeling during fast charging helps optimize charging currents, improving both speed and longevity. In short, using physics-based models provides more accurate predictions, reduces cost, and improves battery efficiency. So, in a nutshell, data access means real-time data. So we are applying the IoT gateway, which facilitates continuous data transmission to the cloud via cellular network, with safety-critical decisions remain localized at the BMS level. We are using secure transmission via MQTT for robust encrypted data communication. We aim to get the granular data, which are transferred to the cloud, so high-resolution data, with adaptive time frequency as well. So if the device is not able to send the data at real time, then it will change the granularity of the data to get the data online as live as possible and not delay up a lot of data transfers. And also the external integration, which is utilizing CAN for the data acquisition and bidirectional communication of parameters, which is essential for machine learning model updates. To harmonize the data, we are using the consistent data formats for easier integration, storage, and exchange between different components of the BMS system. We are ensuring the seamless data consistency across the decentralized system, enhanced by AI-driven analytics for superior predictive accuracy. We aim to get the data consistency by maintaining local models and the BMS level while offloading computationally intensive tasks to the cloud. The collaborative development, which is shared cloud, and the remote experimentation. So real-time cloud access allows teams to test new models and optimize efficiency, improving iteration speed. This is the consortium which is part of this project, and everyone is contributing in developing the next BMS aims. Thank you, everyone. Any questions so far?
Thank you very much, Viral. Actually, I would have a question on how the physics-based model could help optimizing the fast charging conditions to prevent damage to the battery.
So once, let me stop presentation. Yeah. So one example in next BMS is involves the physics-based modeling of anode potential during fast charging. So this is an internal potential which is measurable in commercial batteries, tends to decrease towards zero when high charging currents are applied, which is a condition which significantly impacts the battery lifespan. By utilizing physics-based models, the BMS gains an internal knowledge of the potential, allowing it to accurately calculate the maximum charging current that will bring the anode potential close to zero without actually crossing it. Without this capability, much larger safety margins would need to be applied to avoid crossing this critical boundary, and which would necessarily limit the charging performance and efficiency. So that's how we approach with machine learning to increase the fast charging conditions.
Thank you. Thank you, Viral. Also, another question here on the chat for Viral. Can you provide more details on the real-time characteristics of the cloud connection, the latency, for example? Which model of IoT gateway is used?
So real-time, sorry, provide more details on real-time. So we have the edge device, which is connected in real time with the BMS. So as soon as, so normally in previous, previously what happens is normally a test engineer goes with the car, connects the vehicle with the laptop, and then gets the data, and then comes to the lab, transfers the data to the cloud or to the system, and then does the next steps. Here we are using an IoT gateway which captures the data. It gets the, let's say, in the latency of 1 to 3 seconds, it captures a bunch of CAN frames, and then a parallel pipeline transfers that data to the cloud. And then on the cloud we have the pipeline to decode the data and then give the visualization, let's say more half a second, and then that data will be available on the dashboard directly for visualization. And also, if we are running some cloud models, that data can directly be streamed in to that model for near real-time updates on the cloud models. And the IoT gateway is made during the project, and it is based on Raspberry Pi and other modules with some CAN conversion helping mechanisms.
Okay, thank you. And then one more question to you. How much new additional or array type sensor data as input for physical-based battery model is covered, or just classical VTP per cell?
It is being developed by a partner, not AVL SFR, but I believe we are using a strain and EMB for in addition to the classical VTP sensors.
Thank you. Yes, one more question for you. How are these physics-based models validated? Additionally, can they be transferred to different cell types?
So the physics-based model validation. We have a extensive test cycle. These are we are aiming to TIR4, and it's based on the lab. The physics-based models will be so these are not new LLM models. These are physics-based models, which gets validated by the by comparing or by monitoring the outputs of it compared to actual test cycles. And can they be transferred to the different cell types? I have to check for that. Maybe I can get back to you on that. As it is not developed by me, it's developed by a partner. I maybe connect with them and then give you the update on that.
Thank you very much. Thank you, Vera. I also have a question to Stefan regarding BATMAX and the frameworks and the Fox BMS tool that you showed in your presentation.
Yes.
And I'm wondering under what licenses these are available and how someone either personally or as a company could contribute to those tools.
Okay. So the Fox BMS software is available under BSC 3 clause license. So it's basically usable by everyone for private, commercial, research, and whatsoever purposes. And for contribution, it would be best if people contact us via our homepage, so that we can evaluate how we can incorporate some new features, bug fixes, or whatever people try to commit to our tool. We just want this contact first through email, so that we can make sure that the contributions are well licensed, so that Fox BMS can stay a free and open tool. So we just want that contact prior, so that we can work out how these contributions can happen in a well licensed way.
And can they be integrated with other data analysis frameworks?
Currently, it's mostly driven by our needs, how we have our local infrastructure here, and how big cloud platforms implement tools, for example, like things like Apache, Spark, Hadoop. They are available at basically all big players. So what we are doing is very interoperable and reusable, but some things might be tied to our use case. But we would be very happy to learn how other people would have a use case for that and need to adapt things, so that we could include that in our workflow, of course. So we would be very interested to make the tool as generic and reusable for any kind of battery data.
Thank you very much, Stefan. There is a question to Aurelian. Do they use second life batteries in the ESS infrastructure? Is there a rule of thumb for the minimum SOH at which ESS batteries are replaced, or do they use other metrics for replacement? Aurelian, if you can answer that. Aurelian, you're muted. Okay, I don't know if there is a technical problem, so let's go to the other question and then we come back to this. This question is to Bernhard. Is there any reference to Big Math project from the past as also addressing battery data exchange?
No, but I will have a look at this. Could be interesting.
Okay, and while we are with you, I also have a question for you. How do you plan to scale up the data harmonization process for larger data sets and more complex experiments?
So the thing is, we learned a lot, and people are still creating a lot of data. For the scale up, I think it's mostly on pushing the issue back to the data creators, because I cannot write, or we cannot write always some new formats because people invent new formats. So we agreed in the project now on some common formats for ES data, which for the new experiments is needed to be used by the partners who create the data. So this helps in scaling up. It's not a technical scale-up issue. It's less more organizational, so to say. So this is something we want to do.
Yes, thank you. And I don't know if Aurelian is here, if you can hear us. There are two questions for you here in the chat. It seems that there might be a problem with Aurelian. In any case, I will forward these questions to him and he will be able to answer directly these questions. Maybe a last question on my side, at least to Bernhard, about how you plan to the data ingestion pipeline. How do you envision that the cloud architecture evolving in the future?
So the evolving in the future, it's somewhat related to the other question. The cloud architecture, it's what I said. I don't expect a lot of data in fields of terabytes, so I think this should be fine. What we are thinking of to get rid of this CSV pushing up to the files, because in the end it's quite inefficient and doesn't allow for real-time data. There have been some discussions to push the data
Bernhard, we lost you.
Sorry.
Okay.
I said that we have been thinking, and it's also been mentioned in the project proposal, to implement Apache Kafka to push the data directly and to have a more scalable pipeline. This is something we haven't done so far, because something we learned is that it's too difficult to implement, but it's something we want to do in the project. For a larger scale thing, this is definitely something useful. So if after the project we want to use the project results, we need to have a more scalable pipeline. I think the one which has been presented by Fraunhofer before is also a good example of how you could do that. Our ideas are quite similar to that.
Okay, thank you very much. Just the last try, Aurelian, can you hear us? No. Okay, then, so I suggest that we conclude with this webinar. I would like to thank you very much for the participation and for the speakers for the very nice presentations. We will send a post-webinar survey to have your feedback and opinion on the organization and the content of this webinar. And I would also like to draw your attention that the BMS Alliance have other webinars in this series, and the next one is planned for autumn this year, somewhere in September, October. So just keep in touch with the projects and social media, and of course we will let you know about the next events organized by the Alliance. So I would like to thank you very much again for the participation. and wishing you a nice rest of the day. Goodbye.